Hello, thanks for joining us. So welcome to this AstroPi Mission Space Lab webinar. My name's Dave Honess, and next to me I've got Richard Haler, who's we're both
Hi.
employees of the Raspberry Pi Foundation. And just before we get going, we've got some housekeeping notes to just to go through. If you want to use the chat on YouTube, which should be sort of over here somewhere, you need a sign-in. You need a Google sign-in. So either any Gmail account login should allow you to sign in and participate in that chat. Okay. You can't paste links into the chat. Only we can, and we'll probably be pasting quite a lot of links for you to bookmark. Okay, which is useful information for working through the competition. Try to be on a good internet connection as well, if you can. For example, don't be on a Wi-Fi in a coffee shop somewhere. For example, that will, and you'll be seeing very blurry images if you've got a very bad internet connection and a poor throughput for your network connection. So one of the components that we're going to be looking at today is the Sense Hat, which we'll see in a moment, and it's obviously part of the AstroPi flight units that you've seen before, and you may notice a bit of a flickering problem with the images, but we're not going to use the Sense Hat that much this time, and I'll come on to why in a moment. Last piece of housekeeping is the replay of this webinar won't actually be available on this same link that's just above us. It will actually be on a different URL because YouTube now changed the link when they archive a live broadcast. Okay, so what we'll do is we'll put it on as an update on the astropi.org website. So if you go to the homepage of AstroPi, scroll right down to the bottom under updates, we'll put it underneath there so you can find it to watch it again. Okay, so we've got about 2 hours of content to get through. Okay, so firstly, what I'd like to do is just quickly go through all of the things we're going to talk about. Initially, we're going to oh yes, sorry, I forgot to mention, we're not going to be covering very much to do with the LED matrix. If there is time at the end of this webinar, we covered it quite in detail on the previous webinar, the link for which should be appearing in the chat over here in a moment. And if you want to watch that, that will give you everything you need to know about the LED matrix. At the end of the webinar, if there's time, if we get through everything really well, I might do a quick overview of the LED matrix. But for more information about that link that you can watch there is a slightly earlier version of me explaining how to use it. Okay, so we're going to go through the content of the kit. So we're going to make sure that you've got everything in your kit. We're going to go through all the extra bits and pieces you need. I'll do a quick out-of-the-box setup and guide you through what you need to do initially on the very first setup of your Pi. There's going to be questions in between each of these sections as well, so you have opportunities to ask as many questions as you want. We'll talk about building a 3D printed AstroPi flight unit as well, and then I'll be introducing Python. I'll be talking about the Sense Hat, how to install it, how to program it, how to use the environmental sensors and the movement sensor. We'll be looking at both cameras. Okay, I'll show you how to do the installation procedure for the camera, and we'll record some videos and some pictures as well. And what else will we do? We are going to, and this is probably towards the second hour now. We'll be talking about how to track the ISS offline. Now, one of the limitations that your code has when it runs on the space station is that you don't have an internet connection. Okay, so if you want to know where you are, and pretty much all of the Earth observation experiments this is going to be essential for, you need to calculate where the ISS is using maths. Okay, now don't worry about that too much. It's actually a lot less intimidating than it sounds. There's a pre-written telemetry module which you can just use and plug some numbers into to calculate where the ISS is. So I'll be showing you how to do that. And then I'll quickly go through the submissions process at the end to make sure everybody is aware of what they've got to do to get their code submitted. And then I'll be going through the rules as well, the coding rules, which you must all make sure that you obey to avoid being disqualified automatically. And then if there is time, we'll do some more stuff to do with the LED matrix. Okay? Right, any questions before I get going from the chat?
No, nothing yet.
Nothing yet. Okay, jolly good. All right, so first thing we're going to do is go over to this other camera, and we are going to just make sure that your kit, that everything in it is present. Okay, so and if you find that there's something in my kit that's not in your kit, please send an email to astropie@esa.int, which we'll put in the chat in a second. Okay, so just opening it up, first thing you get is this poster. Okay, so let's just quickly look at this. Now this has got a cheat sheet on it, camera quick reference there, a sense hat quick reference there, and then actually on the inside of it, you have this page, which is the coding rules. Okay, now these are really important, and I would say by about end of December, January, you should have this on your wall. Okay, so that the kids can refer to it and make sure that they're doing everything on this page, and make sure they're not doing anything on this page. Okay. Now we'll go through that towards the end of the webinar, and there'll be an opportunity for everyone to ask questions about that. Okay. So let's put that to one side for the time being. Okay. So the next thing in here, we've got a HDMI cable. Okay. Should be about, I think that's 2 meters long. Yep. You've got a power supply. Okay. Which is a power supply for the Raspberry Pi 3. You should have international plugs in there for those of you who don't have UK plugs, which is most of you. There is a Raspberry Pi 3, okay, Model B, and then you've got both types of camera. So you've got a visible spectrum camera, which is the one with the red camera, and then you've got a Pi Noir camera, which is the infrared capable camera. Okay, and then we have also the Sense hat. Okay. Now, what else have we got? There's last couple of things. So this thing is a HDMI to VGA adapter. So if you've got an old type of monitor, just quickly unbox. Oh, they give you a that's for audio if you want to get audio out of it. So you've got this thing here, which basically allows you to plug that into the Pi, and then the outside on that side you get VGA. Okay. All right. You should also have an SD card in here. All right. And if you open that, you'll find that the actual part that goes into the Raspberry Pi is this little bit at the bottom here, that little micro SD card that comes out. Okay. And then there you have this bag, and that is a components kit which you would use if you were going to build the 3D printed Astro Pi flight case. Okay. And we'll come on to that in a second. Okay. So that's basically the content. I'll just lay it all out here. So you've got HDMI, VGA adapter, power supply, Raspberry Pi, both cameras, and then the Sense hat. You should have all of that in your kit. Okay. So if there's something missing, please send an email to astropie@esa.int, and they'll be able to help you. Okay.
Dave, does that include if people haven't received their kit yet?
Yes, that's also, so they're dealing with all the shipping. So yes, if you can email them about shipping that hasn't arrived yet, they may be able to provide you with a tracking number, which will help you find out if your kit is stuck in customs. So I know some people, I know there's a guy in Bermuda that hasn't had his one yet,
right?
For example, so, okay. Right, okay, so there's a couple of other things that you also need to provide yourself, which is you need a USB keyboard, okay? You need a PC monitor or a TV, family TV, USB mouse as well, and a video cable. If you have a HDMI cable with the kit, if you're using a VGA adapter, you obviously need a VGA cable to connect to the monitor. Okay. So what I'll do now is we're just going to do a quick out-the-box setup next for what we've got in the kit. I'm just going to unbox a few of these parts of the kit now. Okay. Right. Sorry about the banging. Right. So the Raspberry Pi 3, you have this special anti-static paper bag now. And so if those of you who've never seen a Raspberry Pi before, we can just sort of zoom in on this a little bit. So what you've got here, this is actually a full computer, okay? And what you've got is USB ports here to plugging in a keyboard and a mouse. You've got an Ethernet port to get online. Okay. Power is connected through here, so when you unbox the power supply, that will connect to that connector there. Okay, that's the HDMI port for your connecting to your monitor or your TV, and also the port that if I plug in that's the port that goes into, the VGA adapter if you've got old monitors in your school, for example. You've also got a port for analog audio and also composite video. And you've got this big bank of interface pins, and this is how the Raspberry Pi is kind of different from a lot of computers, because you can use these pins to interface with the physical world. Okay, and also that's also how the Pi interfaces with the expansion cards that you add onto it. Other few bits to notice: that's the LAN chip, that's the CPU, okay, and the RAM is on the bottom, that chip there. And that's the SD card slot. Okay, so when you open your SD card, it comes in this adapter so that you can actually put that into your PC and alter the files on your PC if you need to. But when it actually goes to the Pi, you take that and you take that open like that, and then that goes into your SD card slot like that. All right, and then you can now power that up. Okay, now, if you are a VGA user, you may need to force the video mode on your Raspberry Pi. Okay. Now, to do that, you need to edit a file called config.txt. Now, this is done by using the Noobs installer. So the first thing you need to do is allow your Raspberry Pi to boot up, and what you'll see as it's running are a number of logos scrolling on past the screen, and you'll see the Raspberry Pi logo, the ESA logo, the Esro logo, for example, and those will cycle around whilst the OS is installing, and then you'll actually be presented with what you see on the Raspberry Pi desktop. If we just cut to the Raspberry Pi desktop, so this is what you'll eventually get to after the Noobs installer has finished, and this is like the complete. Now you can actually use the Raspberry Pi, but in order to actually force the video mode, there's a file that you need to edit. Okay, and the link of this is going to be pasted into the chat in a second. And if you go to that page, it lists all the options that you need to put into config.txt. Now, what you do is in the Noobs editor, after you reboot, you'll see a momentary screen where it says hold down Shift to enter recovery mode. And what you do is you hold down Shift, you enter recovery mode, and then you'll see the first line is ESA Raspbian. And what you can do is there's a little editor built into Noobs itself, and you click on Edit, and then that presents you the contents of config.txt for that installation of Raspbian. Don't try and edit the config.txt from actually within Raspbian itself, because it won't work. Okay, you have to do it through this Noobs recovery mode. One of the buttons at the top of that screen is to edit the config, and you scroll right to the bottom, and then you can basically input the values which are found in this video mode options link which we put in, and you'll see that there's two groups. There's CEA and DMT. Now CEA is normal TVs like family TVs, and then DMT is if you're using a VGA monitor, that's probably where you're going to find the setting you want. So you would use HDMI group equals 2, and then HDMI mode equals, and then you find the resolution that you want in that list, and that you might need to look up, say for example, the native resolution of your monitor on the internet, and then find it in that list, and then put that number into the Noobs recovery mode, hit exit, and then it will reboot in that mode. Okay, and then that would allow you to force because this VGA adapter is actually quite it's quite dumb. It's quite simple, and the normal HDMI handshake can't see past this. Okay, so what you have to do is force it into a video mode which is compatible with your monitor, and then you can use it. Hopefully, most of you won't need to do that. It's usually pretty good at just working first time. Okay, so Okay, so now we're going to just quickly show you how to connect to Wi-Fi. Okay, so if we just cut back to the Raspberry Pi desktop, okay. So when you get in, I'm actually not on Wi-Fi at the moment, so I'm going to, what you do is move your mouse over to this icon up here, and what I'm going to do is I'm going to select, you click on that and it lists all the Wi-Fi access points that you can, that are available to you. And because we're in Cambridge TV Studios, I'm going to click on this one, CTV, and now I'm going to type in the password. So if you cut to me now, Gmail. Okay, hopefully I've done that right. Okay, so we cut back to the Raspberry Pi now. What you'll see is this icon up here will start flashing whilst it's pairing, and then once it's finished, it stops flashing, and then, oh, looks like my Wi-Fi signal's not that great here, but what I'm going to do is I'm just going to open Chromium and just navigate to a website just to make sure my internet is connected. So there you are, you're now online. Here's the AstroPi website. Okay. All right, and a lot of you may also find that the keyboard setup, that the default keyboard setup for the Raspberry Pis is not quite right for the keyboards that you've got. So what you do in that situation is to click on the Raspberry icon, go to Preferences, and then you go Mouse and Keyboard Settings. Okay, and then you go Keyboard, and then Keyboard Layout down here. All right. Now, for a lot of you, I know there's a lot of keyboards on the continent where the Euro symbol is on number 5 on your keyboard. So if you look at the number 5, if the Euro symbol is on 5, go to United States and then select English US with Euro on 5. That's going to probably be, for a lot of you that are on the continent, that's probably the setting you want. Okay. Obviously, I'm not going to apply this. I'm just going to cancel it because obviously I've got a British keyboard, so I'm just going to cancel this. All right. So, any questions on that before we move on?
No.
No. Okay. All right. Okay. So, one of the things that is quite nice to do. Obviously, on the space station, there are these things. These are the AstroPi flight units that Tim Peake took to the space station with him. There are 2 of them up there. If you go to Google Street View and go on the International Space Station, you can actually see them in the Columbus module. Okay, so if you select the Columbus module and then sort of pan down and to the right, you'll see them both there. One of them's got a green screen and the other one's got a blank screen. It's one of the really kind of engaging things about AstroPi is that you know the students get to have and operate and play with the same hardware that's on the space station. Okay, so it's an optional activity that you can do if you want to, but it's not necessary. You can actually go off and 3D print your own AstroPi flight unit, and I've got one here which I'm using, which I'm going to be using throughout the webinar today. But that's what they look like when they're completed. And if I just hold it up next to the actual real flight unit, you can see that they are pretty much the same. They are based on the same CAD with some slight differences. Okay. Obviously, it's a lot lighter as well because it's made out of like 3D printed plastic. And obviously, that's what this bag is for. Okay. I just want to stress that it's not compulsory. You don't have to do it, especially if you're quite limited on time. But it is a really nice thing to really kind of cement the engagement of your team to know that they're really able to prototype and test what it's going to look like when it's on the space station. Now, if you go to the AstroPi website, what we have is an educational resource. If I scroll right down, here it is here. So the 3D printed AstroPi flight case is just under here. You click on that, and this will take you to the instructions for how to build the flight case. And there is even a nice video which you can follow. Okay, and there's a couple of out-of-date bits on that now, which I'll mention in a minute. The first task though is to actually download the CAD. Okay, now if you just go to your browser and you type in rpf.io /APSTL, like that. And then that will take you to a GitHub page where you can actually download these STL files. Okay. Now these are the official ones that you should use. There's a couple of old versions of the CAD flying around on places like Thingiverse, which you shouldn't use. You should only use the version of the CAD which is available here. And you essentially can just download these files and feed them into your 3D printer, and out will come the parts of the 4 parts that you need to build the AstroPi flight case. Okay. And then this video, Richard is going to about to paste a link in there in a second. If you don't have a 3D printer, there is a alternative. You can actually just order prints online. If I just go here, there's a really nice website called 3dhubs.com, and what this does is it puts people in touch who want 3D printing done, and you can find someone local to you who can make the parts for you and post them to you. Okay, and that obviously costs a bit of money, but you know, it will be cheaper than buying a whole new 3D printer, for example. Okay. All right. So yeah, so just make sure that you use these versions of the STL. There's actually 2 versions. There's this version, and there's also an anti-warping version. And these anti-warping printed parts are mainly for if you've got a 3D printer that doesn't have an oven around where the part is printed. Because what those ovens do is they keep it at the right temperature so that the plastic doesn't like warp and bend or anything as it's cooling. And this one I've got here actually has got some quite bad warp on it. Actually, if I just hold it up like that, I don't know if you can see that. It looks like it's a little bit bent. So even if you do get a few bits of warping, you can still, like, you know, these 4 bolts in the corners just pull it all right at the end. But what these do is, if I just load one of these, you should be able to see. I'm not sure if it's going to actually load or not. Oh, no, it looks like it's not going to work. But if you do that yourself on your desktop, you'll see a 3D model appear. And what that does is, around the feet, around the actual corners, there are these like discs which jut out. You can almost see them in this picture here. These discs cut out, and what they do is they keep some heat in, basically, and that allows the plastic to cool down more slowly, and then it doesn't sort of lift up and curl upwards. Okay. All right. So just to stress it again, it's a non-compulsory activity, but it's something that you know, most schools, like, kids are always looking for an excuse to get on the 3D printer, and this is like the perfect thing to let them do it. They'll learn a bit about additive manufacturing in the process, and then you can follow all these steps and follow the video as well. Okay. And one quick side note about the way this all works is that the joystick of the Raspberry Pi is going to it changes orientation. So what normally happens is, when the Raspberry Pi is used, you'll see this when I install the SenseHat, the Raspberry Pi's normal up joystick direction is that way, up here. Okay, but when it's actually installed in the Raspberry Pi, the SenseHat is sideways. So up is still this way, if you know what I mean. Okay, and then down is that way. So you just have to program your program to compensate for that, which is pretty easy to do. You just you know, just look for the up event when you want when you want left, for example. Okay. All right. So any questions on 3D printing or anything like that?
No, we've only got one question, which is where can people find the links after the YouTube stream's finished?
Okay. What I might do is I might publish this. I've got a program document which I'm working to, which I'll put that up along with the replay. So when you go to this update section here at the bottom of the AstroPi website, and you know, Paolo and Tamara are going to get shunted along a little bit here, and a new tile will appear, which will be the replay of the AstroPi of this webinar, and I'll put a link to the PDF which has got all my links in it. Okay, and then you can download that PDF, and hopefully it will remind you of what we went through. Okay. Is that the only question?
That's it, yeah.
All right, okay. So next thing I'm going to be doing is introducing the Python programming language. Now, I imagine that a lot of you have probably done something with Python before, but there will probably be a few of you that haven't done anything with Python before. And what I've got, a while ago when I first joined Raspberry Pi, I wrote a little resource, which is a little guide for how to get into Python if you know Visual Basic. I know a lot of teachers have done Visual Basic because they've done it in Microsoft Access or Microsoft Excel, for example. You use Visual Basic macros and stuff. So this is a handy little URL. The link's going to be pasted into the chat now, which will basically show you the Visual Basic code and then the equivalent Python code, if you see what I mean. So for example, here is like a bit about variables. So you've got how to define a counter. You know, here for example in Visual Basic you've got dim count as counter, but in Python you don't actually have to define the variable. It's all done by assignment. So the moment you actually just assign a type to a variable, it becomes that type of variable. For example, you don't need to do double or boolean or string. You just define it like that, and that's how it works. Okay, and then you've got indentation. Explains about indentation. So if you've never touched Python before, but you have done a bit of Visual Basic, come and have a read of this, because this will kind of like point you in the right direction and make you feel a little bit more comfortable about diving into Python. Okay. And there's also a free course available as well, which if you want to do a bit more, Code Academy have got quite a nice Learn Python course, which you can go and do. And that's free. The link for this will also be in the chat in a second. Okay. All right. So what we're going to do is we're going to use something called idle, which is a Python programming integrated development environment. So if you go to programming, hit the Raspberry. Oopsie, let's minimize that. Click the Raspberry, go to programming, and then underneath here you'll see Python 3 idle. Let's just click on Python 3 idle, and then this will bring up, this is what we call a shell. Okay, now this is like a command prompt almost, if you know what I mean. You can actually start typing code into here. I can type in like print hello, and it prints hello. I can do 2 + 2, and it gives me the answer. Now this isn't where you would type your code. Okay, so this is actually more of a debug tool really. What we normally do is we write all the lines of the code that we want to run, and then we run them all at once, if you know what I mean. So what we usually do is we go to File, New File, and then here we have an empty program which we can type code into. For example, now I can do things like, you know, print hello, and then Dave equals 2 + 2, print Dave. Okay, so if I just run that now, you have to always save a Python program when you run it. So save Dave, and then we can just run that, and then you get the output in the shell. Okay, so that's basically the concept. You write all the lines of code that you want to in one go, and then you run them all together, and then it will quickly switch over to the shell and give you all the output for your program. All right. So any questions?
Got a couple of questions on Python. First one is it easy to learn Python if you've done some C++?
Oh yeah, yeah. If you've done some C++, you're like completely set up. Python is actually a lot more simple than C++ is. It's actually it's an interpreted language. It's not as efficient as C++. In terms of its memory management and things like that, but the actual syntax is really clean. So, for example, it's a good first text-based language for young people. What we like to do is we like to see kids by the time they're in secondary school learning a text-based language. What we don't want to see is kids leaving school at 16 and only having done Scratch, for example, or block-based languages. And then what happens is they go to college and they get hit by Java and then they quit, right? So this is a really good stepping stone into more advanced languages. So for example, like if you just look here, the concept of indentation, we don't have like begin and end tags. What you have is like, you use spacing like that. So you've got this if statement here with a colon after it. And then you have these two, usually we use 4 spaces or a tab to indent, and then that means like if count equals 0, those 2 lines would run, else those 2 lines would run, for example. All right. But this resource that I wrote a while ago, it's useful if you've done a bit of Visual Basic, and if you've done C++, you've got no problem basically. You'll jump right into it really easily. Okay.
One more question about Python, which is about using additional libraries, so additional PyPy libraries.
Yeah,
and
you can
one
totally
particularly
do that.
around if my team's using TensorFlow, how can we install it?
Usually, what you do when you want to install a module, it's usually done via the terminal, and we'll be doing a module installation later. What module was it exactly?
A TensorFlow module. So.
Oh, okay, yeah. I'm not familiar with that module, but usually it's just it's you go up to the command line here, and then it's usually sudo apt-get install, and then whatever the module name is, or you can do sudo pip3 install, and that's pip for Python 3, and then the name of the module. Usually that's what it is. It'll be something like that for that particular.
And will
module.
those then get installed on the AstroPis on the ISS?
Yes, so I'll come on to that later as well. So there's going to be a special field on the form, on the sign up form, where they've got to type in all of the commands, terminal commands that are required to install their prerequisites. Okay.
One final question, which is why should we use Python 3.4 if on the Raspberry Pi 3.5 is available by default?
Because Python 3.4 is what's on the space station, and we haven't updated it to 3.5 yet.
Good answer.
Okay. All right. So, any other questions?
No, that's it on Python. Yeah.
Okay. Right. Okay. So, what we're going to do is next thing we're going to do is we're going to install the Sense app on the Raspberry Pi. Okay. So, I'm just going to go back over to this other camera view, and I'm going to show you how to unbox and install the Sense app. So, let's make a bit of space here. Right. Okay. So, you take your Raspberry Pi, and then you should have a Sense app. Open that. Okay. Then you have an anti-static bag, and inside that you have your Sense app. Okay, now usually they also give you these little bag of screws. Okay. Now these are standoffs. Now I haven't got a screwdriver, so I'm not going to install them all, but these are quite simple to do. What you do is you take your Raspberry Pi, put a screw through the bottom of one of these 4 mounting holes, and then what you can do is hold that there with your thumb, take one of they've got screw threads on both ends, okay, and then you essentially just screw it on like that, okay, and that's one on there now, okay. I'll do that for the other one. Okay, so there you go. So I'm just going to do the 2 on this side. That's the minimum I would always recommend. And you can use this to secure, put all 4 in if you want to, but I'm just going to, for time's sake, I'm just going to put the 2 in. And then what you do is, the Sense app comes with this header pin, or header plug on the bottom, and essentially all you have to do is just, you line these 2 up together. Try and do it so you can see it better. And like that, and that will fit in there like that, and all you do is just, and that's it, okay. And then because I've just put those 2 in as the minimum, that's the plug keeps it rigid on that side, and those two standoffs keep it rigid on that side. And then if you want to, you can also put the screw in the top as well to keep it nice and secure. All right. And I recommend you do this with the Raspberry Pi turned off. Okay, I wouldn't recommend you do that with the Pi plugged in. So shut it down and unplug everything before you do this, okay? All right, now what I'm going to do, I'm going to see if we can zoom really far in now. Can we get really close in on this Sense app? A bit closer. Let's move over. Okay. All right, now what we're going to do, I'm just going to quickly walk you around the features of the Sense app so you know what's on it. Okay. First thing, obviously, is this big bank of LEDs. Okay, so you've got 64 RGB LEDs, and when you're explaining this to your students, get them to think about these things as like they're giant pixels, basically. Okay, so they each, inside them, they have a red LED, a green LED, and a blue LED inside each cell. Okay, and you can program that to show all kinds of text messages, icons, like you can do a little Pac-Man on there or whatever you want to show, and that's basically your only display. Okay, the Astro Pi on the space station is not plugged into any kind of HDMI monitor or anything like that. Okay, so this is your display, and you have to get the kids to think about how they're going to use that on the space station. All right. Okay, this little silver thing down here is actually a joystick. If I just turn it like that, you can see that it protrudes up a little bit, and it's basically a 5-button joystick with up, down, left, and right. Okay, and then also you can click it as well. It's got a center click. Okay, and those on your Raspberry Pi will be mapped to the cursor keys and enter. Okay, and then if you look closely over here, you can just about make out the word humidity. I don't know if you can see this on however good the quality is on your stream, but that sensor there is a humidity and temperature sensor, and there's a pressure sensor just here as well. It's these little chips are actually the sensors, and then that one there that I'm touching is the actual an all-in-one accelerometer, gyroscope, and magnetometer just in that chip as well. All right, and then you've got a little there's an Atmel chip which is driving the LEDs, and a LED driver chip, and then you've got that's the ID EEPROM which identifies it. Also, that chip there is an identification EEPROM which the Raspberry Pi uses to know that a sense hat has been plugged in, sort of thing. Okay. Now, when you first plug this in, you'll see like a rainbow pattern come up on here when you first apply power to it. Okay, and what will happen is after a few moments that rainbow pattern should disappear. Okay, now if you're in a situation where the rainbow pattern doesn't disappear, okay, then you might have a connection problem between the sense hat and the Pi. Okay. Right. So, a quick side note: we do have an online emulator for the sense hat, which allows you actually to do sense hat programming without a physical device, actually just in the browser window. Okay, so I'm just going to quickly go back to the Raspberry Pi and show it to you. I'll just go over here. So I'll just load this. The link for this will appear in the chat in a second. Okay, now this is basically what you have. It loads usually with a demo piece of code. And it's a little bit slow on the Raspberry Pi because the Raspberry Pi is not going to be as powerful as your desktop computer, for example. And then you see here it's actually running some code in the virtual sense hat. And this is sometimes good if you want to set homework for the kids. You can actually, if they can't take home the kit because you've only got one kit, and they're only going to be doing something which is going to be a bit of code which you then contribute to the main body of code for the experiment, you can set them some work and get them to use the sense hat emulator at home. Okay. All right. So the other thing I'd like to show you is the full coding documentation for the sense hat as well. So this is a page which your students will hit all the time. So if we just quickly go to this page, the link's going to appear in the chat as well. This is a really useful page, pythonhosted.org/senshat/API. This gives you all the Python coding functions and what you can do with them, and even little sample bits of code that you can just copy and paste and try into your, like for example, I'm just going to copy and paste this bit. This is the set pixels command. I'm just going to copy and paste this into idle, and I believe what this does is it creates a little question mark on the LED matrix. And let's hope that you can all see this. Right, I'm just going to run that now. Just call it test. And that's what you can do. So if I just hold that up, I'm not sure how well you can see that. It might be a little bit dulled out by the brightness of the studio lights, but you can see there's a question mark on the LED matrix. Okay. But that's what you can do. You can basically just come in here, take a piece of code, and then just copy and paste it to test out what that particular command is doing. Okay. it's a more comprehensive version of the poster that you've got with the kit. Okay, so it's something definitely you should bookmark and definitely pass on to your students. All right. Okay. All right. And there's one other thing about the SenseHat programming library, which you might find interesting as well, is that it is possible to translate the coding terms that are used, and you'll see in that previous link the words used to actually activate the functions of the SenseHat are all in English. Okay, so it's things like set pixel, get accelerometer, you know, flip horizontal, flip vertical, get pixels. You know, this is all in English. Now, what I've had some feedback, particularly from teachers from the network of Esro offices that ESA runs, that it would be a removal of a barrier if we could potentially have the coding terms translated. Now, I haven't sorted that out, been able to sort that out for this competition, but I have made a start. Now, I'm just pasting a link into the chat now, which is this forum link I've got. Now, what I've done is I've started up a way of using Python code inheritance to actually translate all the coding terms. And what I've done is I've got a gist here, a GitHub gist. I'll just go to that. This is something that you could bundle with your experiment. And it basically allows you to translate all of the coding terms and use a translated version of the API. So, for example, what I've done is I've just put en underscore in front of everything to demonstrate the concept. And what happened is a friend of mine who is French did a French version. And you can come down here and look at the French version. And this would then, for example, you'd be able to use like, for example, things like that. For flip vertical, you can get reflexion vertical, for example, and then those would actually be the words that the kids would be typing in as they're coding. Okay, and it just increases the level of intuitiveness. Now, if you wanted to do this for your own language, you could take one of these and then basically adapt it for your language. Now, the difficulty of doing this is that you need a bilingual programmer, really, to be able to correctly identify what would be an intuitive word to use instead of like flip H, for example. So that's why it's something that I do want to actually get built into the SenseHat. Okay, and then I think what he also did was he gave an example, a trinket code which has got an example of what the consuming code would look like. So, for example, if I just load this is the kind of thing that. We just wait for this to load for a second. Yeah, for example here, what you've got is sense equals SenseHat underscore FR, and then sense.official message, and then the message, if you know what I mean. So, and then all of the actual coding terms can actually be translated into your own language. But what you'll have to do is, if you want to do that, you're going to have to go off and potentially start from one of these GitHub gists and actually re-implement it with your own language. And then what you would do is when you submit the code, you would supply it to us with your version of the translation. Okay, and then that would actually fly to the space station as well. Okay. All right, so that's the SenseHat all installed. And are there any questions about any of that? About any of the references or the translations or anything?
We've got one more question back about Python, the
Okay.
TensorFlow library. So in this case, the person's saying that the TensorFlow library is only available through PyPy for Python 3.6. If they need to install it on an older version, it's lots of manual configuration and compilation.
Yes, I'd recommend not using that library then. We'll try and find an alternative to using it. Because if it becomes a complete nightmare for us to install it on the ISS, it will just won't be possible. Okay. All right, so what we're going to do then is we're going to move on to, I'm just going to do a few example programs now in Python, just showing you how to use the environmental sensors. Okay. So you've got temperature, pressure, and humidity. They're the three main principal environmental sensors. So I'm just going to start a new program. Now, whenever you do a sense-hat program, you always start with from sense_hat import sense hats like that, and then you have sense equals sense_hat. And what we're doing there is that's importing the library, which allows us to talk to the sense_hat, and this line is actually creating this thing called sense, which is an instance of the class, which lets us actually activate the function. So we can now go sense dot, show message, for example, and then that will then scroll a message on the LED matrix. But what we're going to do is I'm going to actually just, for example, just now I'm going to look at the humidity sensor. So I'm going to go while true. This is like a quick program you can use to demonstrate the sensors to your kids. Print sense dot humidity, like that. And all that's going to do, I'm going to save that as hum. It's just going to basically show repeatedly what the humidity measurement is. So if I just run this, it'll switch back to the shell and start printing out the measurement. Okay, so you can see there's like a ridiculous number of decimal places as well. So it's saying it's about 39%, 40% humidity in this room at the moment. So one of the other things you can do is if you want to just trim it off, you can go round sense.humidity, comma 1 or something like that. That'll be round it to 1 decimal place. All right, so let's run that again. Okay, so you see it's just in an infinite loop. It's just constantly printing out the humidity value, and just to show you that it is actually measuring the humidity in here, I'm going to exhale into the Raspberry Pi so you can see the number change. There you go. You can see actually that it jumped right up to about 180 something, and now you see it slowly dropping back down to normal. Okay. Now I think I might have a slightly dodgy sensor, so they're not supposed to jump up to that much. If you get that behaviour as well, you might have a broken sense_hat. Okay, so I would watch. If you get very sharp jumps in it, you should be able to do a really long breath on it and see it go up slowly. You may want to look at getting a new sense_hat sent out to you. Okay, so that's basically what we're doing there. It actually saves it as a number. So, for example, we can do things like this, like H equals round humidity. And then print H, for example. And then what you can do is you can start doing things like if H greater than 100, print danger, or something like that. Whatever you want it, whatever you want to do. So if I just do that. There you go. See a bunch of dangers came up. Okay. So that's basically what you do. You actually, the product of that function is a number which you can store in a variable and then start doing stuff with in your code. Okay. So there's also a pressure sensor. So I'm going to use the same technique. And obviously what you can do is anytime I'm talking about these things, you can come and find the function in here as well. So for example, I'll just quickly come and find the humidity. There's get humidity. You can use get humidity, but I prefer to just use the property version of it, where you don't have to use the brackets, for example, like that. So what I'm just going to change this to pressure now. Okay, and that will actually now access the pressure sensor. Now this isn't something that I can change really unless I put the Raspberry Pi inside a plastic bag and start. Oh, I'm not printing. That's why. Let's change that to P. Print P. Run that again. Okay, so that's about right. It's in millibars, so it's 1015 millibars, which is just a little bit above what you would get oh, our TV's just having a problem for a second there. Can you see if you can press the button? It's about to power itself off. Oh, there you go. Thank you. Right, there you go. Okay, so that's basically how you access the pressure sensor, and there's also a temperature sensor as well. You can actually just get that by using, I'll just change that to T. There you go. Now you can see it's definitely not 35 degrees in here, right? Now, one of the things that you need to be aware of with the sense_hat is that in whatever configuration you've got, especially in this kind of configuration, what you'll have is there is actually a degree of thermal leakage from the CPU into the actual temperature sensor. Okay, now you see the temperature sensors are just here, and the CPU is just underneath it there, and the CPU actually generates heat. All CPUs do, and you know, those of you who've got PCs, you'll know that there are fans and everything inside your PC to keep everything cool. And what actually happens is, and this is actually a slight design flaw with the SenseHat, and because the units that went to the space station have it, we decided that it's important for everyone else to be able to have the same, be exposed to the same problem, so that if it's going to affect their science, they can try and do something about it. So that's the sensor. The humidity sensor is the one that I was just accessing, and what happens is the actual fill of the circuit board is a conductor, and what we should have done is really pulled this thing back a bit. And the reason we haven't fixed the design or anything yet is because this is still exactly the same as what's on the space station. Okay, and what you can do, it does help a little bit because you've got a Raspberry Pi 3, which is actually different to the one on the space station. The one on the space station is actually a Raspberry Pi 1B+, which generates a little bit less heat. So this effect is a little bit less pronounced on the one on the space station. And obviously the Raspberry Pi 3 is a lot faster. It's about almost 10 times faster, which is also a consideration for how you program your code. You don't want to code something that's really kind of ragging the processor, for example, because then on the Raspberry Pi on the space station it would go a bit too slowly. And we test all that obviously when we judge your code. But yeah, so just remember when thinking about the temperature measurement that you will be getting some thermal leak from the Raspberry Pi CPU. And we have had experiments in the past where students have attempted to kind of calibrate out the error by measuring the temperature. Okay, but well, you can use, for example, the CPU temperature and its usual kind of expected delta from ambient as a way of working out what kind of where around ambient should be, and then use that to kind of calibrate out the error in the temperature sensor. So this is something really important to consider if the science you're doing is reliant on temperature, and specifically using that sense.temp method to get the temperature measurement. Okay. So those are the three environmental sensors. You've got temperature, pressure, and humidity. You can look up the references on here, and then you've got temperature. You can actually also get the temperature from the pressure sensor as well, and there's a special function for that, get temperature from pressure. There's some example code for that there. So those are the three sensors, and obviously please bear in mind the limitation of the temperature sensor. Any questions on that?
There are. So first one is there a limit of how many sensor measurements we can expect to take in 1 second?
There probably is, but it's the limit of how fast your code can run, if you know what I mean. There's no actual kind of, there's no restriction on the poll time. In actually like a physical restriction or a hardware restriction. It will basically keep reporting the measurement to you as fast as you can run your code, basically.
Right.
Yeah.
And one more, which is, do the thermometer, humidity sensor and barometer measure the data only at the station, or is it possible to get measurements from places on Earth too?
Right, yeah. So they only measure their physical locality. So they'll be measuring the conditions right where the Astro Pi actually is. And if you look at the actual Astro Pi, that little hole above it on the front there, that's not the camera hole. Okay, that's the hole for it's an air hole which is right above the humidity sensor. Okay, and the camera's on the bottom. Okay, and so yeah, so it'll only measure the temperature and the conditions, the environmental conditions inside the space station, right where the Astro Pi is. Okay.
And final one is, how warm will the Pi 1B get?
Usually it gets the CPU temperature.
I guess,
yeah, it usually gets up to about 32, 33, something like that. It actually, CPU load affects it. So if you're running a bit of code which, and you can do this because there's a command that you can use to which is actually mentioned in this poster. There's a command you can run on which will give you the CPU temperature. And then if you, for example, did something which was quite CPU intensive in your code, you'd see the temperature going up. So you can affect it by what you're doing in your program.
Right.
So yeah.
That's it for questions.
All right. Okay. So we're going to move on to the IMU sensor, which is probably the most fun one because it's probably the one that your kids are going to have most excitement out of, because it's essentially measuring acceleration, angular momentum, and the Earth's magnetic field. So what we're going to do, the first thing we've got, there's a really nice demo that you can run, which will help your kids understand the principal angles of pitch, roll, and yaw. Okay, so if we just put the camera on me for a sec, what I'm going to do is we're going to this is a nice thing you can do in the class to help them understand what pitch, roll, and yaw means. Okay, so start off with pitch. Pitch is like a plane taking off, like the angle of a plane as it lifts its nose. That's pitching up. Okay, so if you think about the Earth's axis, right, getting them thinking about axes is a good thing. So think about the Earth's axis, and the Earth rotates around its axis. Okay, now in flight there are 3 axes that all cross in the middle, if you see what I mean. So pitch is that if you imagine the axis is around, like running right through your waist, and you're tipping forwards and backwards around that axis, that's pitch. Okay, so like if I picked up the Raspberry Pi here, you know, that's the axis of pitch, and if I do that, that's the pitch axis, for example. Okay, now yaw is like steering a car. So if you imagine the axis going down through my head, and then we rotate around the axis like that. Okay, all right, and that's like, and then for example on the Raspberry Pi that would be that kind of motion. Okay, so that's yaw. Okay, and then roll. If the axis was going right through my chest and I rotated around it like that, that's roll. Okay, and then on the Raspberry Pi that would be that motion. Okay, now if you know those 3 angles, you can describe the orientation of an object in 3D space basically. So if I go like grab it and move it in any orientation, say pick that one, okay, from standing I can do a bit of pitch, a bit of roll, and a bit of yaw, and I get it back into that position, if you see what I mean. So you can describe the orientation of an object by using those 3 values. And on the sensor gives those angles to you in 0 to 360 degree values. Okay, and we'll get into that in a minute. But it's really important that you help the kids understand the principal angles of pitch, roll, and yaw. And what we've got is a nice little demo that you can just download. It gives you 3D graphics and everything, which you can then run. So what you do is you go to the terminal icon, which is this little black icon up here. Okay, and then you're going to type in some commands, and these will be pasted into the chat as well. Okay, so git clone http github.com/astropi/Apollo Soyuz. Okay, and what that's going to do is now going to pull down this demo program from the internet. All right. Now it has a prerequisite, which is something called Py3D, which is a little module which you need to install. Now here's an example of how to install a Python module. Okay, so sudo pip3 install Py3D. Okay, and that's actually going to install the 3D module that this code depends on. Okay, and just wait for that to happen. All right, cleaning up. Okay, so there we go. Right, and then all you do, you should find that now you've got a folder called Apollo Soyuz. There it is. Okay, so cd, and then we can run soyuz.py. So /soyuz.py. All right. Okay, and on a Pi 3, this should take about not very long. So this is what you get. This is actually a 3D model of the of when the Apollo and the Soyuz spacecraft met in orbit for the first time. And basically what it does is you can pick up your SenseHat now on your Raspberry Pi, and you should see, as you move it, the model moves in exactly the same way. Okay. Okay. So, and essentially what you can do is, what you do now is get the kids to try and make it do the pitch, roll, and yaw movements. Okay, so let's just start off with pitch. Now, the SD card slot of the Raspberry Pi is the booster. Okay, is the rocket booster of the Apollo module, and the USB ports are where the Soyuz module is. Okay, so if I just pitch up the Soyuz module like that, you can see it's tilting up like that. Okay, so that's pitch. Okay, now if I do yaw, which is like twisting it like that, you can see I'm twisting it like that. That's the yaw motion, and then the roll motion is going to be that motion. You see it's rolling. Okay, and that's quite a fun thing to do in class, so that they all just get the concept of pitch, roll, and yaw. Okay, so they know what orientation actually means. You see what I mean? And then it's escape to get back out of it. All right. Okay. Okay, so let's start off with a quick program, which is just going to display the orientation. Okay. So I'm going to go back to the Python shell, and I'm just going to minimize the browser, start a new program, new file. So from sensehat, let's see, move that out a bit. Sense equals sensehat, and then I'll do my while true again. This is like the forever block in Scratch if you've used Scratch before. So print sense.orientation. Nice and easy. Now what this does is actually going to give you what we call a Python dictionary object, which I'll explain in a second. But if you just run this program, it's probably going to fill the screen with what almost seems unintelligible, but I'll hopefully be able to show you what it means. We start running that, and you can see you've got this pitch, roll, and yaw with numbers there. And if I start moving, for example, in the yaw direction, you can see the yaw value is changing. Hopefully that's coming out on the stream okay. All right. So what you can do, for example, if you're only looking at what this is what we call a dictionary. Okay, and it allows you to access each of the values that are inside here using the word that's associated with them. So you've got roll, colon, and then the value, yaw, colon, and the value, and pitch, colon, and the value. And the way you do that in the code, if I just did something like this, I could go O equals sense.orientation, and that's taken a copy of the current orientation and stored it in O. Okay, and then I can go, say P is for pitch, I can go O open bracket pitch, and that's now taking a copy of what pitch was and sticking it in P. And then we could do the same for R for roll, O roll, and then Y for yaw. Okay, and then I could do something like this, print P R Y. Oopsie. There we go. And that's actually just ripping out the numbers as raw numbers. Okay. Oops, I spelled pitch wrong. P-I-T-C-H. There you go. There you go. So now it's actually pulling out the raw numbers of what's in there. Okay. So that's basically how you access the orientation values, and what you need to do when you're using this orientation function, you need to understand that it's based on what we call a Kelman filter, okay, which is basically behind the code here. What you don't see in your code is that it's actually keeping the pitch, roll, and yaw angles as numbers in memory, and then as measurements come in from the sensors, it keeps updating them in memory. So what you need to do is poll the sensor really fast, okay, because otherwise it won't keep up. So for example, if I go import time up here, and then I go down here and I go time.sleep 5, what's going to happen is it'll only actually update the angles in memory every time I read the orientation. Okay, so what will happen is if I put a time delay of 5 seconds into this loop, you'll find that you'll get lag. Okay, the actual values reported will lag behind the actual measurements that, the actual movements that the sensor is doing. So you should never really, when you're doing stuff with the orientation, because it works in this way where it only updates the angles in memory every time the sensors are read, you should never really put a time delay in that kind of loop. Okay, so let me just show you. If I let's put 1 second in. What I'm going to do now is, you can see that. Now if I just rotate I'm moving it in the yaw axis, you can see that it's actually, I've done almost 90-degree turn now, and you can see that it's really kind of lagging behind. Okay. So a thing to never do is to have a time sleep in a loop where you're measuring orientation, purely because, you know, whilst the delay is happening, these angles don't get updated. Okay. Now, is that clear? Have I explained that well enough? Has everybody any questions?
I think so.
Yeah. Yeah. Okay.
There's one question. Someone was interested in measuring angular velocity, so they want to know how the Astro Pis are actually attached inside the ISS.
Oh, okay. Right. Okay. Yeah. That's good. Quite a good thing to go on. If you go onto Google Street View and look at the Columbus module, you can actually see how they're attached. And on this Pi doesn't have it, but on this plate here, normally an interface plate is actually installed on here. And what happens is they attach it to essentially what they call it a multi-use bracket, but it's like a dog leg arm. And then what happens is that arm holds it rigid, and then the bottom end of that arm is clamped onto something else. So it's actually physically mounted to the bulkheads. Okay, so as the ISS moves, and if the ISS changes course, it will affect that sensor. Okay. Now the problem with orientation also, this particular way of working, is that it drifts unless you've got 1G. If you don't have 1G giving you a direction of down, the actual orientation can drift unpredictably. Okay, so I wanted you to be aware of it because it's actually quite a fun thing to do on ground. But on the space station, I don't recommend using this orientation function because it doesn't have 1G. The sensors are actually almost reporting nothing in some cases, unless, for example, there's a force of acceleration on the space station, like if they're firing the thrusters. But yeah, so that's something to be aware of. Like, there's some data logging you can go and look at actually, which if I just quickly go to the AstroPi website and you scroll down a bit here, there's this flight data analysis resource. If you click on that, and there's some data logging that was done for this particular resource, which you can look at to characterize the kind of measurements you can expect. If we go to where can I get the CSV files, you can download some long-term, like there's a 4-week-long one there from Ed in Columbus of just constant sensor measurements of all the sensors. So this is like a really nice way to be able to characterize the kind of sensor measurements and the range of those measurements that you can expect to get when your code is running. Okay, so you can just come in here, click on download, and it will basically download you a zip file inside which is a huge CSV file. And what I would do is chop that up into small chunks if you're going to look at that data and analyze it. But that's a really good thing to do, especially if you want to find out what you can really see how the orientation drifts by looking at that data. All right, so that link will get pasted into the chat, but you can also go and just you can quite easily find it on the homepage of the AstroPi website. So that's that resource there. Okay. All right, so what I'm going to go on to next is the discrete sensors. So the actual what this is based on, the orientation function is it uses all three of the IMU sensors. So acceleration, gyroscope, and magnetometer are all used to give you this pitch, roll, and yaw angles. But if you don't want it, if you know this isn't exactly that reliable for you on the space station, you might just, for example, just want to look at the accelerometer. So let's just look at the accelerometer. If I go A equals sense dot, I think it's Excel. There's a shortened version of it, which is Excel, and then print A. Oopsie. This is now just talking to the accelerometer. Actually, no, sorry, it's Excel raw. That's it. I think let me just check the API. Go down here. IMU sensor. Oh yeah, there you go. Yeah, Excel raw. There you go. All right. So what that'll do is that reads only the actual accelerometer. It ignores the magnetometer and gyroscope. And then this is the kind of measurement you can get back out of it. And you can see there it's giving you X, Y, and Z as opposed to pitch, roll, and yaw. X, Y, and Z don't really mean anything in pitch, roll, and yaw don't really mean anything in terms of like acceleration, because what you're talking about is the actual acceleration relative to the device itself, and the device itself is. So if what I'm going to do is, if you just watch this, hopefully this is okay and it's not looking too bad on the stream. I'm just going to shake it in the Z orientation. You can see like at the moment Z is giving you about 1. It's about 0.99. But if I shake it in that duration, you might see some like large numbers come up there. So if I just do that, you can see. I might see if I can just quickly pause it after doing that shake. There you go. So you see, I managed to get 3 Gs out of it there. So each of these measurements is in Gs. So by shaking it, I managed to get a 3G value there. Now let's just run that code again, and what I'm going to do is I'm going to show you that you can transfer that. Normally in normal gravity you have 1 G of acceleration, and that's the force of gravity is trying to accelerate us to the centre of the Earth, if you see what I mean. So that's why you're getting close to 1 G at standing rate, if you know what I mean. So if I just quickly run this again. So the Z-axis, if I just quickly point to the camera now, if you go back to the overhead camera, on that particular, the Z-axis is straight down through the pie like that, okay? And then the X-axis is that one, and the Y-axis is that one, okay? So if I just, what I'm going to do, I'm going to go back to this one now, and I'm going to, currently it's 1G in that, and now if I invert the pie, turn it over, you've got minus 1G in the Z-axis, okay? So that's the force of acceleration going straight down. So that tells you which way the direction of the Earth is, if you see what I mean. But obviously on the ISS, this won't work. You'll get pretty much 0 for everything when this has happened. So if I go in that direction, I've got 1 on the Y-axis, okay? And now if I invert that, I'll get minus 1 on the Y-axis, almost minus 1. I'll get it exactly right. And then if I go on that orientation, I've got 1 on the X-axis, and then flip it again, and then minus 1 on the X-axis. Right. Now, that might be useful to you in your experiments, and obviously this one doesn't matter if you pole it slowly. Okay, if this one, if I, for example, put a delay in here, that doesn't affect it because it's not doing the Kelman filter. It's not updating some angles in memory. It's just measuring the raw data off the sensor and reporting it to you. Okay, and for example, like if I only wanted to look at the Z-axis, it's exactly the same. It's like a dictionary object, so you can do it like that, and that will now only print out the Z-axis. Okay, so there you go, and then I can invert it and get you minus 1G. And then if I shake it, I should be able to get the sort of like the 3G sort of like effect. There you go. So, oh wow, I've got minus 4Gs then. That was good. Okay. So you can show all that, and just to show the characterization of that sensor. Okay. Now, to show you the gyroscope, it's basically, we try to make the function names all nice and intuitive. So I'm going to go G, and then gyro raw. Okay. Now the gyroscope gives you angular velocity in radians per second. Okay. Now, this is probably a little bit more advanced in terms of like what the measurement means. So some of your older kids will probably want to do this. But if you just run this, you can see that, and then you can see as I'm moving it, the values are all changing. Okay. So that will actually give you as the moment you stop, right, it should all pretty much go back to 0. Okay, so it's only reporting something when we're turning, okay, when we're actually moving. So the moment you stop, everything goes back to 0. And that's what that sensor does, okay? Now, on the space station, I have seen a team once try and use this to calculate the actual orbital angle. And what you do is that all of these sensors will have a bit of noise on them. And if you look at that flight data analysis data, that CSV file you can download, you'll see that there is like a noise floor. And sometimes the measurements don't peak above that noise floor, which basically makes it meaningless, if you see what I mean. So for example, the accelerometer data, you might find that you don't get a decent value out of it unless the station is the thrusters are being fired, or an orbital reboost is happening, or something like that. So these are all things to think about when you're programming what your sensors are going to do. So the other sensor is the magnetometer, and I think in the code it's called compass. If I change that to scene, I mean you don't need. You can call these anything if you want to. I can call them Dave if you want. Print Dave, and I'm going to call that compass raw. Now this is going to give it to you in, it's X, Y, and Z again, but this is in, I believe it's nanoteslas. I'll just check it's a bit further up here, isn't it? Compass is in, oh, microteslas, sorry, microteslas. Okay. And I haven't actually got a magnet here. I should have brought a little screwdriver with a magnet on the end, because then I can wave it around. But that's quite a nice thing to do, actually. If you've got any kind of screwdrivers with a magnet on it, or anything like that, have this kind of thing running, and then get them to wave a magnet over it, and you see the numbers going crazy. Okay. I can sort of affect them by obviously the Earth's magnetic field will affect it. So by turning the Astro Pi around, I can actually make the measurements all change, because the Earth's magnetic field is changing orientation as I relative to the device as I move it. But having a little magnet on the end of a screwdriver or something like that is quite a nice way to sort of perturb it and see it change. Okay. So, are there any questions about the IMU sensor?
We've got one which is, how does the gyroscope work?
Ah, yes. So this is it's an area of computer science which I don't know a huge amount about, but it's basically down at chemistry level it works at. And what it does, I believe, what you have inside that little chip which is there, there's a tiny little chamber with some noble gas in it. And what happens is, as you move, the noble gas is like heavy, if you know what I mean. And what happens is gravity pulls the noble gas, pulls it down, and then the sides of the chamber can actually measure where it's going. I believe that's how it works, but there's probably someone in the chat who's going to be going, no, that's not how it works. But
no one yet. No.
No. Okay, but I believe it's like that. The actual, that's, right down at transistor level. That's chemistry basically, and it's an area of computer science that I'm definitely no expert on. All I know is you type in these commands and it gives you numbers back, which is basically what the kids need to know to be able to do their science. Okay. Any other questions?
No, that's it.
Okay. All right. So next thing we're going to do is we're going to move on to the cameras. Okay. Okay. So what I'm going to do first, when you want to install a camera, one of the things I would suggest to do is to remove the SenseApp first, so you can get at the camera connector. I'm just taking that SenseApp off. And when you want to remove the SenseApp, don't rip it off at an angle, because you can bend the pins. What I tend to do is just rock it back and forth like that. Keep rocking it, and it should just come loose. You can see I've got a little bit of height on it yet. And just be careful you don't try and pull it off straight like that. You don't want to bend any of the pins on either end. Okay. So when you unbox your cameras, you'll have two types. They each come in a little anti-static bag. Okay, that's the first one. And each one has this little tab on there, which is just to protect the lens. You'll have to rip that off, okay? So that's the visible spectrum camera, okay? With the green circuit board, okay? Now, the infrared spectrum camera has a black circuit board, like that. Also with the little tab which you have to remove. Okay. Now also inside your anti-static bag you will notice that there is a little blue thing. Okay. Now please don't lose this. Okay. Now those of you who are going to be doing Earth observation experiments, this filter is actually going to be installed on the bottom of the Astro Pi on the space station. Okay. Now what it does, it specifically permits a kind of Earth observation technique which permits vegetation analysis. Okay. It blocks visible red, and you can see there like the red looks much darker of the Raspberry Pi case there. It blocks visible red and green, okay, but allows through infrared and blue, okay, which is why it looks blue, okay. And what you can then do is, because you can look up online about how to use this technique, but essentially it allows you to measure the difference between the reflected infrared light and visible light from living green plants, and then you can do some post-processing of your images to work out where the most healthy plants are on ground. I know quite a few people are going to be using that. So if you're going to be using the Pi Noir camera, okay, which is on Astro Pi Izzy, please make sure you don't lose this blue bit of plastic. Now if you've got a kit from last year and you have lost it, please send an email to inquiries@astropi.org and we can send you another one. Okay. Right. Okay, so there's one thing which I need to show you before we get into installing them. I'll show you how to install them on the Astro Pi in a minute. There's a couple of things I need to show you about the differences between the cameras you've got and the ones that are on the space station. Okay, so if you go to this link, we're just going to paste this into the chat now. This is a documentation page of the Raspberry Pi website. It gives you the information about the cameras that we've got. Now, the cameras in the kit are camera module V2. All right, so you'll have this camera, but the ones on the space station are camera module V1. Now don't worry, any code you write is going to be compatible with the ones on the space station, but there are slight differences in the capabilities of these two cameras, okay? So for example, you've got an 8 megapixel camera, but the one on the space station is 5 megapixels, all right? And they have different resolutions. For example, this one, that's your native resolution, and the ones on the space station are of that resolution. So if you're taking pictures, that's the res of the pictures you can get back from the space station, okay? So it's important to understand those differences and make sure that you, for example, don't try and put that resolution into your code and like hard code that into your code, because that then won't work on the ones on the space station. Okay, so make sure you come here and look at this page and just make sure when you're using the cameras, you're not going to do anything which is going to be sort of sabotaged by it being on having to run on a camera module V1. Okay. Now, one of the other things you may want to do is calculate ground sampling distance. Now, this is something that most, especially if you're trying, I know there's just a couple of experiments where people are trying to work out how fast the ISS is going by looking at the speed at which things move on the ground and how fast they move past the window, for example. Now, there's a nice little tool you can use, which is is it here? Yeah, there's a GSD calculator spreadsheet which you can download. Now the link for this will get pasted into the chat in a second. But you can go here, download this in Excel format, and then all of the values it needs here, like the sensor width, the focal length, the actual height in meters, you can just use 400 kilometers for that as a rough guess. And then the image width and the image height, you can get off this page, okay? And then you can plug that into this Excel sheet, and it will actually, it's got all the maths and everything already there for you to work out the ground sampling distance, which is how much distance on ground each pixel is worth. And I did this a while ago, and I worked out that the camera module V1 in the horizontal plane was 161 meters per pixel if the ISS is at 400 kilometers in height. Okay, so if that's a necessary part of your experiment, go to that link, download that Excel file, and then you can use that to help work out the maths for it. All right? So the main difference between these two cameras, they're basically both identical, but normal cameras, this one's much, the visible spectrum camera is much more like what you have on your mobile phone camera, okay? And that has what we call an infrared exclusion filter, okay? And this one basically just doesn't have that exclusion filter, okay? So infrared light can actually go into that camera and be seen by it, and it gives you kind of like a bit of a peculiar effect. You can see infrared light at the same time as visible light, and we'll see what that looks like in a minute, because the unit that I've got wired up here has the Pi Noir camera in it. Okay, and you'll see the effect of that. We can find a TV remote. We can fire the TV remote at the camera as well, and we can actually see what that looks like. Okay, so if those of you who are going to do radiation dosimetry experiments, I want to just quickly go through a quick side note for those of you who are going to do that, because I know there's a couple of people who are wanting to use the camera sensor as an actual a radiation dosimeter. And what we did is this was actually done during Tim Peake's mission. Okay, and what we found is that there is I recommend anyone who's doing a dosimetry experiment can come to this URL, which is going to be pasted into the chat in a second, and have a look at this project, because this was actually this was done during Tim Peake's experiment. And what they actually took their Raspberry Pi along to a radiation laboratory and fired a neutron cannon at it to see what would happen. And you can see these images of what they got. I'm not sure if that's going to work, if I can just view that as raw. Yeah, you can see these kind of like specks. And what happens is when an ionizing piece of radiation is hitting the camera sensor, it thinks it's seeing light. It's actually charging up the capacitors of the camera sensor. And then what they did is they wrote some code to count the specks. Okay, so have a look at what they did. And what happened is they actually, oops, I've closed the thing. What actually happened is they actually they got a null result. Basically, the theory is that this thick aluminium case kept out a lot of the radiation, because the camera sensor is actually right inside there, and obviously it's got like thick aluminium in all directions, and that may affect your results if you're doing a radiation experiment based on the camera. Okay, so just something to bear in mind. Okay. Okay. So, quick note also about the infrared camera. This cannot see thermal infrared. Okay, thermal infrared is a different part of the IR spectrum, and you can't pick it up with this camera. So if your experiment requires optical measurement of temperature on ground, this camera can't do that. Okay. So you'll have to, if you may need to revise your experiment proposal, okay? And if you need to do that, contact astropie@esa.int, and they'll be able to, help you with that. Okay. Right. One other thing as well is I want to show you there's a filter, the blue filter, which I've shown already, has there's a nice diagram you can look at online, and the link for this will be put into the chat now. And this basically gives you, this line on this graph gives you what the line of what is let through and what is not. Okay, so you can see here it lets through a lot of blue, it comes down into green, stops letting through anything in green, orange, visible red, and then as it goes back into infrared, it starts letting stuff through again. Okay. All right. And what that allows you to do is if you, for example, for each pixel, you can look at how much infrared and how much visible light is represented in that pixel. You'd ignore the green channel completely, and then you can actually do a bit of calculation to work out how much chlorophyll is going on in that pixel, and that's how you can then do like a false recolor of that pixel when you post-process your images. Okay. All right, so that's a nice introduction to both cameras, and we're actually going to do some programming now and show you how to use them. So before we get into the programming of how to actually use the cameras, are there any questions about the introduction I've just done?
No.
No? Okay, cool. All right. So what we're going to do now, I'm actually going to quickly show you how to install it. That's what I'll do. I'll show you how to actually install the camera module itself now. All right. So if we go back to the overhead, now the camera connector is this one here. Okay, and you can see if you look closely, it actually says camera on the circuit board there. Now ignore this one up here. This one's for a display connector. Okay. Now we do make like a flat screen, a touch screen peripheral, which is used on this port. But do not put a camera in there. Okay, because you might actually kill the camera. All right. Only put the camera into this one. Okay. Now what you do, take for example the Pi Noir one. Put that one to one side. You'll notice that on the ribbon there's a blue tab. Okay, and then on the opposite side there are some little tin connectors. Okay, and all you do, the tin connectors have to face away from the Ethernet port. Okay, so what you do, this tab lifts up like that, and then it rocks back and forth. And then what you do is you just take the tin connectors, pop them in like that. And what you want to do is you want to make sure that they're nice and level. Okay, and then push them down. Push those two tabs back down, and you'll see it will get a little bit tight there, and that's it, locking it into place. Okay, and then just check when you're done that all those pins are nice and level. And that's basically, obviously do this with the Raspberry Pi off, please. Don't do it with it on, because you could kill the camera as well. That's the camera now ready to go, ready and installed. And if you want to have the sensor on as well, you can see that there is a little ribbon there, a little hole for the ribbon. So what I'll do is just show you how to do that as well. So basically what I would normally do is feed that through first. Don't install the sensor yet, then connect it. Oopsie, bit of a fiddly job. And then what you've done, once you've got that in, you can then feed that back through, like so. And then pop it on like that. Okay, and then that's how you can use your camera and the sensor together. All right. Okay, so what we're going to do, we're firstly going to start off with taking a time-stamped picture. Okay. Now what I would do, any pictures you take on the space station, you're going to be running on Astro Pi Izzy, which is going to be deployed on a hatch window. Okay. Now, some of you will have probably noticed this. If you go to your desktop, just minimize all your windows and you right click on the desktop, you can go desktop preferences. You should all have this. There are some images up here which are actually about of the Astro Pis on the space station. So there's one actually here of the Raspberry Pi actually mounted on the hatch. Okay, so that's what it will look like. This is actually how they're physically mounted onto the stations. You see, it's just been clamped onto the handle for the hatch, and basically behind that door is space. Okay, and the actual Pi the camera is going to look straight down at Earth, and what we call that is a nadir angle. Okay, and you are essentially going to have your code running on that Pi on a hatch window like that. Okay, we're going to look into getting like a shroud that goes over the top of this, so that those of you who are doing nighttime observations can get images with no reflections. Okay, so just if you want to have a look at that, you can go and do that. So what we'll do now is I'm going to just quickly do some coding to show you how to actually access the camera. Okay, so programming, Python 3 idle, file, new file. Okay, now one of the things you might want to do is make sure that your time is accurate on your Pi as well. That might be something that you want to do, because if you any Earth observation, I highly recommend that you make sure that the time is recorded with the image, so that you can work out the location of what that image is. It's absolutely essential for any kind of Earth observation. Now, when you're developing your code, what we can do is force a time sync. Okay, now these commands are going to be put into the chat. Okay, especially if the Raspberry Pi itself doesn't have a real-time clock. The ones on the space station do, and that's because they need to keep their time if they're turned off. But the ones that you have, they're programmed to always just get the time from the internet every time they turn on. And obviously the Raspberry Pi is supposed to be a very costed down device. So what we do, you can type in these commands to force a time sync if your time seems to be inaccurate. So sudo service NTP network time protocol stop the NTP service, and then what we do is we're going to have to install a little program called NTP date. And what that'll do, that's going to go off to the internet and install this program. It's now pulling it down. All right, and then what we can do is we can just go sudo ntp date pool.ntp.org, and that will actually go off and find an NTP server, a network time protocol server, to get us the time, and then it should give you a little report by how much it adjusted the time. There you go. Oh, we were quite accurate anyway, so that's fine. So that's basically what it's done, set the time, then you type in date like that to get the time as well. All right. And what I would do is, you can do that on your local Pi if you want to, you know, just make sure if your time's not right and you want to force a time update, that's how to do it. So sudo service NTP start as well, and then that makes it work in the background. All right. Okay, so first thing we're going to do is we're going to do a time-stamped picture. Okay. All right. So I'm going to start a new program. Now what we do now, we go import Pi camera, import time, and then I'm also going to import date time, which is another module. These should already be installed. You went, oh, as DT, and these should already be installed on your Pi. Okay, I'm just going to save that. I'm going to call it cam1. Now what we do, create like the Sense app, we're going to go cam equals Pi camera dot Pi camera. Okay, that creates this thing called cam, which allows us to poke the functions of the camera module. Just like the Sense app, there's also a big list of functions as well. So if I just this link will be put into the chat as well, which you've got the full API references, but you've got the basic recipes and stuff like that as well, which you can go and look at to get all these code examples. But I'm just going to carry on here. So I've created the camera module, and then I'm going to go cam.start preview, and then I'm going to go cam. Well, let's put time.sleep 5 cam.capture. I'm going to call it dave.jpg, and then cam.stop underscore preview. Now I'll show you. We'll just capture an image on its own first, okay? And the preview is basically going to cause the screen of the Raspberry Pi to show what the camera can see. Okay. Now have we got that remote control somewhere? I'm just going to show what it looks like when you fire a remote at it. Actually, if I just do that now, if I just run the code. So now if you just fire that remote, you can actually see that. That's quite a nice thing to do in the classroom, to show them that you can actually see infrared light being emitted by a TV remote. Okay. Right, now I'm going to go and find that file. So I need to open the file browser, and there's dave.jpg, and you can see that's the image. A bit blurry because we were I wasn't really holding it very still, but you can see that's the image. Okay. Now what we want to do is actually apply. There's a couple of things you can do. You can either make the file name the timestamp, or you can actually embed the timestamp in the image data. And a way to do that is use this datetime function. There's a way to do it where you use this thing called string from time. So if I do if I, for example, do str time equals dt.datetime.now, and then strf time. Now what you can do is you put the time format into there, and that will basically what we call a format string. Now there's a link which I can show you, which gives you all of the information about this, which is, here it is. I'll wait for that to stay. So these are all the values you can put in, these percent things. They allow you to build up the string format that you want, and then when you run that code, it will return the values. It will substitute these percent values for the actual time string that you want. So let's do an example. If I just do, for example, %d is the day, %m is the month, and then %Y is the year. And then if I do hour, minute, second, h colon %m, and then colon %s. It's like that. And then what I can do is I can then do, for example, capture str_time plus JPEG, like that. Okay, and that will create the time now, create the format based on probably not use slashes. Let's use underscores. That's probably a better thing to do. And then probably the same thing with colons. You don't want these in file names. And then you can run that, and then when that takes a picture of me, I'll just do it like that. 1, 2, 3, 4. Now we should find that I've got a file which is named the actual date. If you see what I mean there, you can see the actual file name is actually the date. And that's quite a nice way of doing it as well. You can do it that way. But you can also, if you want to, annotate the actual image itself. Okay, so what I'll do is I'll put that back to dave.jpg, and what we'll do is I'll make this a more sort of human readable date, and then use colons there. And what you can do is you can actually use this annotation function where you go it's cam.annotate_text equals, and then str_time. Okay, I think you need to set the background color for it as well. You need to go cam.annotate background equals pyCamera.color. Oh, it's COLOR, sorry, black. Like that. And then that should then give us the time on the preview. Okay, you can see it at the top there, and you can actually make it bigger if you want to as well, which I'll do now. You can just go cam.annotate, oopsie, text size equals, say, 50. Run that again. You see it's a bit bigger now, right? And then what will actually happen is when that picture's taken, you can go and look at it. It says dave.jpg again. The actual pixels of the image have the actual data encoded into it. Okay, and that's a really good way, because sometimes when pictures are brought down from the space station, they get renamed. Okay, and it's a good way to ensure that any information that you want to stay with that image stays with that image. If you see what I mean. Usually they do provide us a little CSV file which contains the original names, so I can usually get back to the original names before we send the data back to you. Okay. All right, so I've also got a couple of other pre-written programs which, because we're sort of starting to run out of time now, I'm going to just quickly go through some other pre-written programs that I've got. So let's go, where have I got it? It's in Documents, Code, Camera. So I've got a time-stamped image template which I wrote earlier, and what we've got here is essentially what we just went through. A little trick you can do is alpha equals 192 when you do the start preview, and what that does is it actually makes it translucent. And I've also, what you probably would have noticed in that previous program, the actual date wouldn't have been exactly right for when the picture was taken. So in this one I've done a little for loop, where I update the text of the annotation every second before the actual image is taken. So if I just do that now, you'll actually see the annotation text changing as I run the code. Oh, okay, I know what's happened there. I've got the got to close all of the shells. Right, let's run that again. Okay. Okay, you can see it's like translucent. You can still see the shell through the image, and you see the number at the top was changing there. And then I should have foo.jpg there as well. There you go. Okay. So the actual image you get won't be translucent. It's only translucent so that, for example, if you this will happen in your class. If I'm just going to type in wibble here, which is going to cause it to runtime error. What will happen is your code will get a runtime error, and they'll get stuck on the camera preview, and they won't be able to see what's going on. Okay, and the camera preview stays up then. Okay, and what you can actually do is when you can type in cam.stop_preview manually into the shell, and then get back to where you were. Okay. All right. So what else have I got? I've also got a video as well. You can also record videos. Here's a quick demonstration of a video. I can put these code files up on the update page as well, so you can get these examples. Your quick sheet that comes with the kit also has some of this stuff in it. But basically, what I've got here is a quick program which is going to show record a quick video. Oh, I've got that. If you get this error, it means you just need to close your Python shells. It means you've got multiple shells open that are using resources. Okay, so just close all your Python shells and then run it again. So this is actually going to record a video to a file. So I'm just going to, you can see I've got some annotations there. There's Richard waving. Okay, and then we're just going to wait for this to finish. There you go. And then what we've got is I've got foo.h264. Now what the camera does when it writes video, it creates this h264 file. Okay, and what it is, it's like an MP4, but it doesn't have any timing data in it. Okay, so if I went to there's a command line tool you can use to play it back. If I just there it is there. It's called OMX Player. And if I go OMX Player foo.h264, and you'll see what happens is it plays it back fast, like too fast. Okay, and that's because it's got no timing data in it. Okay, it's got no sound data in it either. Okay, so it's obviously not. It's almost like an incomplete video. But what you can do is a couple of tricks you can use to fix the video so it plays back at normal speed. Now these are some commands that are also going to be popped into the chat, which you can type in. Okay, I think I've given them those. Oh no, I might not have given you those. Okay, so don't worry about that. So I'll type them in here. They're actually part of my. What we're going to do is going to install this thing called gpack into. Yeah, this is actually a little tool that you can just run. Oh, failed to fit. Oh, I need to go sudo apt-get update. If you get any errors like that, always run this update command, which actually refreshes what's on the remote server. Let's just hope our internet connection here isn't too slow. I'll do that periodically on any Raspberry Pi that you own anyway. And then what we're going to do is when that's installed, I'm going to run this command here, which is basically going to convert it into an MP4. And then you can potentially, export that to put it on social media or wherever you want to put it. You see what I mean? Come on. Right, so I'm going to run that command now. And then that's going to basically just quickly... Oh yeah, sorry, I need to install the gpack, don't I? That now needs to be installed. Yeah, so do the update first, then do the gpack. And then I can run that MP4 box command. So this is basically how you install new software on the Raspberry Pi, running these apt-get install commands. All right, now I can run that command. There you go. Right, so now foo.mp4 should be there. So now if I do OMX player again, but instead of foo.h264 we do mp4, it should play back properly. You see that's now at normal speed. You see the seconds ticking by properly. All right. So if you are recording videos, also please bear in mind that you're going to use up a lot of disk space. Okay, so just be considerate about how much disk space you're using, because the space on the ISS is shared with other teams, for example. Okay. All right, now I've got some example imagery as well. If there's any other stuff you need to know about the camera, there's all these basic and advanced recipes you can go and look at. But I've got some example images which I'd like to share with you as well. If you actually want to characterize the kind of images that you're going to expect back from the space station. Okay, so if you go to, firstly, we've got a previous experiment that was done during Tim Peake's mission, where they've got about 4,000 quite low-res images taken. The link of this is going to be pasted into the chat. You can actually look and see the kind of images that you can get back from the space station on here. If I click and open one of these, hopefully it will load. There we go. There you go. So that looks like some mountains maybe. So yeah, be aware, especially if you're doing anything like OpenCV or anything like that, that you probably will see the hatch window in the picture. Okay, and you might want to, for example, try and program to cater for that. Now these are really low res images. These are like 640 by 480, but you will get the full resolution of the camera when you take your pictures. Okay. Now you'll probably notice if you load some of the earlier pictures here that we're getting bad reflections. And now this particular experiment didn't need nighttime images. Okay, and I know some of you will be only focusing on nighttime images, and what we'll have, we are actually going to have a big sort of shroud which goes over the top of the pie on the hatch, big sort of almost looks like a witch's hat almost, that goes over the top of this, and you see these tape marks of wherever it's been used before, and that will basically stop any light that's in the module from reflecting on the window and then ruining your nighttime images. Okay, so you should be able to expect to get really nice high quality images of the ground and be able to see all the light and everything that's coming from them. Okay, now with the filter, these images were taken with the Pi Noir camera but without the filter. Okay, and that kind of almost ruined this guy's experiment because we didn't include it in the payload. But he was able to come up with a different way of processing the images to get at the information that he wanted. But what we've got also is there's another URL you can go to see what some images look like when they're using the camera, using the blue filter. Okay, so this link will be pasted into the chat in a second. And you can see this is what they kind of look like when they're... This was taken from a drone, these pictures. They're not actually from the ISS. Okay. And you see they do look kind of peculiar. And if you scroll down a bit further, you can see some of the post-processed images they've been able to make with it. Okay, so this is obviously highlighting where the most chlorophyll's going on up in the trees and not so much down on the ground. Okay. All right, so the last main topic I want to cover, and I know we're gonna have to overrun a little bit because this is really important, is how to track the ISS.
Before we go on, Dave, is there any questions on photography?
Yeah,
okay.
I'm going to just go before we go. Yeah, let's have questions.
Okay, so first one is, how do we use the visible light camera to measure light levels?
Ah, right. Okay, so if you're going to do something like that, what you need to do is basically take the picture and then post-process the picture. So you capture the picture, get foo.jpg or whatever you're going to do, and then you can load it using something called Python Pill, which should be supplied with it. And then what I would do is you could do something simple like an average color check. But what you need to do is load the picture and then delete the picture. Okay, one of the rules is, we're going to go through the rules in a minute, but one of the rules is that you're not allowed to have images returned to ground from the visible spectrum camera in Columbus, and that's for reasons of crew privacy, because a lot of the medical experiments take place in the Columbus module, and for that reason we can't have imagery being returned to ground from that camera. But you can do things like just take the picture, load it using Python Pill and convert it to, say, just RGB data, and then loop through all of the pixels in the data and work out the average color. And the higher the average color, the more bright it's going to be. There might be a code example of that in this. I'm not sure. Let me just check and remind myself. No, it's not in there. But I haven't got a code example I can lay my hands on quickly. Yeah, if you just look into, let's just quickly Google it. Let's go. Oopsie, don't want two of those going. Pill or pillow, yeah. There you go. Go to this URL, pillow.readthedocs.io, and then this will give you some examples about how to, you know, load images as RGB. I just sort of convert to RGB, see if anything like that's in there. There you go. There's some results there that you can go and look at, and essentially that's how I would do. There's also a way you can look at luminosity data with the camera module as well. Actually, if you go to, I think it's under Advanced Recipes. Yeah, you can go. Oh, probably spot luminosity correctly there. Okay, so. Yeah, the advanced modules have got, there are some ways of reading raw data. Here you go. This an unencoded YUV image is probably quite a good way of doing it, because then you can look at the luminosity and chrominance levels of the picture. That might be a good thing to look at. And then there's some example code for how to do that here. Okay. Any other questions?
Yeah. Are there any instructions as to how to add false color to each pixel for photosynthesis investigations?
No. Well, the thing is, I haven't got any, but there are some previous examples of code that you can go and look at which have done it. You can just search on, if you search on NDVI, which stands for Normalized Differential Vegetation Index. That's the scale that you can calculate based on the product of the blue filter. There's a nice Wikipedia page on that which will tell you what's going on and how to actually calculate it. And I'm sure you can find some previous examples of code which will point you in the right direction. But what I would do is to use something like, for example, Matplotlib is a good library to do that, and you can load the pixel data that you've got from your JPEG into that, and then lots of tools are available in Matplotlib to recolor it based on a scale that you define and a color gradient that you define.
Okay, good. So you mentioned OpenCV earlier on.
Yeah.
So I was asking, is OpenCV, are the Python libraries already installed on the Astro Pi?
No, they're not, but we will install them. Well, assuming that we get entries that want the OpenCV library, we'll install whatever the latest version is.
And the question around installing libraries was, if you've got your 3-hour code execution time, does installing extra libraries go towards that 3-hour period?
No.
Okay.
No. Yeah, we'll install the prerequisites prior to your code running. Actually, all the prerequisites are installed as part of a script which runs when all the code is deployed on the space station.
And final one was, what is the range of frequency that the IR camera can register?
Good question. I don't know that actually.
I was Googling, I couldn't find the data.
I wonder if it's on here.
No, it isn't. I looked.
Oh, is it not on there? I don't know. I think it's up to about 900 nanometers. I think it's about that. I'm not entirely sure actually. but I can find out, and if drop an email to inquiries@astropie.org with that in it, and I'll ask one of our engineers tomorrow and get back to you.
Great, that was it.
All right, okay. So this is the last. If we've still got some kind of like we're actually at the time you scheduled to end this, but what I'm going to do is we're going to just press on and just do this how to track the ISS whilst offline, because it's a really important thing, and those of you who are doing Earth observation images, it's basically essential for you. Okay. So what we're going to do is firstly let's talk about what we call two-line element telemetry. Okay. Now this is basically. I'll just quickly go to the. There's a branch of orbital mechanics which allows you to basically, if you know the speed and trajectory of an object in space and where it was at a particular time, based on the current time, you can then extrapolate its path, and taking into account the rotation of the Earth, you can work out when in a future time where that object should then be, if you know what I mean. And that's basically what we're talking about when we say telemetry. It's actually a way of predicting the future location of the space station based on a known speed, trajectory, course, and where it was at a particular time. Okay, and we call this the two-line element telemetry. Okay, and it's published online by NORAD. Okay, which are tracking North American Aerospace Defense Command, or something like. I think that's the acronym for NORAD. Someone correct me in the chat if I'm wrong. And what they do is they track everything that's in orbit, and then publish these two-line element sets for every object. And if you go to this URL, this CellStrack URL, that's going to be pasted in now into the chat. You get this big list of these just what looks like gobbledygook numbers. Okay. Now, essentially, what it is, each 3 lines gives you the telemetry for one particular object in space, and the first one is usually always the ISS because it's the most important. Okay, and each of these numbers means something different. Now, if you go back to the Wikipedia page and scroll down, you click on Format there. This gives you what all of the numbers are in each one. So you've got the title line, which usually just gives you the name ISS Syra. And then you have all these other fields down in below, which are things like the designator, the epoch, and the start time, and all this kind of stuff. And then you've got line 2, which gives you the satellite number, the inclination, the eccentricity of the orbit, all that kind of stuff. Now, this is a secondary school project, and this is university level maths, so you don't actually have to get your kids to understand what's going on here, but what you need, what they can do with it is they can actually use and consume this and use the actual product of the maths. Okay, so what we're going to do is we're going to show you how to write some code which will calculate the ISS location. Okay, so what we're going to do before we do that, I just want to quickly show you a couple of things about the orbit of the ISS as well. Now, this URL is quite a nice one because it's got some nice pictures which illustrate how the ISS orbits work. So if I'm just going to come down here, I don't need you to read all of this, I just want to show you some pictures. Now, this is go back down further. There we go. Now that's the picture I want. So the ISS orbit is inclined relative to the Earth, relative to the equator, at 51.6 degrees. Okay, so basically what happens is that dotted line there is the space shuttle, and this dotted line here is the space station. Okay, so what if you've got 51.6 degree inclination, that means you cover ground which is 51.6 degrees above the equator and 51.6 degrees below the equator. So that those two red line up there is as far north as the ISS ever gets, and that red line down there is as far south as the ISS ever gets. Okay, now if you go down, you probably see a lot of images like this where you've got this like S shape, and this is to do with map projection. Okay, and essentially you can see there that line up there where each of the S's curves off is 51.6 degrees north, and then that line down there where they all curve back up is 51.6 degrees south. Okay, so if you're trying to study something that's outside of that location using Earth observation, you're going to be out of luck. Okay, because you won't see it in the image. The camera is going to point directly down at the Earth. Okay, So and this is a nice picture that illustrates it. You see, as the Earth rotates, every orbit is going to cover a different ground path. Okay, so as it goes round, as the Earth rotates around, you see that we cover a slightly different ground path every time. But what never happens is the ISS never goes north of this point. So for example, if you wanted in your experiment to study something in the North Pole or Greenland or something like that, you're never actually going to fly over that area. Okay, and the same is true for the Southern Hemisphere. Okay, so it's important to get the kids to understand that, so they know the limitations of what they're going to be able to see in the pictures that you get back. And also remember that you've got 3 hours of runtime, so you're only going to get 2 orbits, which is 2 of these S shapes. Okay, so you're going to get one up there and then the next one over as well. Okay, so you won't get global coverage. Okay, so you have to think about, say for example you wanted to get Earth observation pictures of Europe. Okay, it might be that when you run, your orbit misses Europe completely. Your 2 orbits miss Europe completely. So pick targets that are, pick some other contingency targets that you could also work with. Okay. All right, and that URL is just, you don't need to read all this. I just wanted to show you these pictures because they kind of illustrate the point I'm making really well. Okay. Now to consume this information in Python, we need to install a module called Ephemeris. Okay, so we're going to come back to the terminal again, and there are going to be some commands that get pasted into the chat. First thing we're going to do, sudo pip 3, which is to install Python modules for Python 3, install fm, E-P-H-E-M, fm. Okay, and just run that. Now this is actually going to do some code compiling now. So this will actually take a few moments to run. And you see when these things here, this ARM, Linux, stuff like that, it's actually compiling code here at the moment, okay? And you just don't worry about what all this means, just let it run. Okay. And what this is doing is actually compiling binary code to make this nice and fast, basically. Lots of code that this is dependent on is written not written in Python, it's written in C and C++, and that's why we're having to compile it to binary, because Python's an interpreted language, C and C++ are compiled languages. So just need to wait for this to finish. It'll take a few moments. Hopefully you don't get a horrible error at the end of it, which is going to be awkward if we do.
I'm confident. There you go.
There we go. Right, okay, we're good. All right, and then you can go pip3 show fm, and then what you should have is version 3760. There you go, that's the version you want to make sure you've got, because that's the version on the space station. All right. Okay, so the other thing you can do is, whilst we're doing this, because I'm going to basically write some code which is going to give us the latitude and longitude of the ISS based on these numbers. What you can do at home is you can load this URL, which is an ISS tracker, and that will give you the location of the ISS. Now, when this loads, you can see it's giving you the night and day time, and it gives you the current orbit and the next orbit, I believe. And the numbers that we're going to calculate are here: longitude, that 102 up there, and then the latitude, that 10.141. Those are the numbers we're going to calculate based on the programming I'm going to show you now, which gives you the ground location over which the ISS was at that current time. Okay, so just remember that the stream is on about a 20-second delay. Okay, so when you actually see this, if you're running this locally to the stream, what you see in the YouTube feed is about 20 seconds behind real time. Okay, right. So let's start Python again. Programming Python 3. And what we're going to do is file, new file, and then the first thing we need to do is to get those. We're going to import FM, import time. Right, and then what we're going to do is we're going to grab those. We're going to go to cells-track.org. This information is actually updated for almost every orbit by NORAD. So if you come in here, you can refresh this. Now, the first question, there's probably going to be a question in a second about how are we going to, if we submit our code in February and our code only runs in April, it's going to go out of date, right?
Someone's already asked it.
Okay, right, yeah. So what actually happens is, when I see you using this in your code, we have a way to update the telemetry from a shared location on the Raspberry Pi, which our ground station keeps up to date. And what they do is they will update this every couple of days on the Raspberry Pi on the space station, and I'll modify your code slightly before it flies to load the telemetry from that location. Okay, so you can expect when you run your code on the space station that you're going to calculate accurate locations. All right. So first thing you do, go and grab those strings from that website and pop them in here. We're going to create strings from them. So I'm going to go name equals that, line 1 equals that, and line 2 equals that. And obviously, whenever you have a string, you have to have the open and close quotes. Okay. Now, we're going to create a variable called ISS, which is the ISS object, and we're going to go fm.read TLE, which is the 2-line element telemetry, and then you just go name line 1, line 2. Okay, and that's it. That will then load these numbers into this thing, which is called ISS, which we can then, in the same way as we poke the camera module, the cam and the sense of the sense hat and camera module, it works in a similar way to that. So now what I'm going to do is I'm going to go while true ISS.compute, and that's basically going to compute the location for the current time, and it's based on the system clock of the Raspberry Pi. Okay, now we keep the ISS Raspberry Pis, the Astro Pis, they're synchronized to GMT. Okay, so you can make sure that, and obviously the this telemetry is based on GMT as well. So what I'm going to do, I'm just going to go print ISS.sublat and then ISS.sublong. And those are the two values. Okay, and then I'll put time.sleep 1. In fact, what I might do is make this a little bit, it might make this a little bit easier to see. I might just go and put a string here and do lat colon %s long colon %s, and then substitute those values into that string. All right, now if you will open that ISS tracker and watch this, this should be accurate when I run it. There you go. So that's where we are right now. So if I'm going to go and load that tracker. Right. Okay, so it's a little bit different. Oh, it's about right. That one's. It seems like the ISS tracker here is actually a little bit ahead of us. So I wonder. Actually, I wonder if we're ahead of it actually. Oh no, yeah, it looks like it's ahead of us. So basically, it's. I think there's a slight difference. It's with how this website calculates it, but you can. We are doing it as accurately as can be, but you can see that these are about right. Okay, and it will look a bit different to you on the stream. Okay. All right. Now, what I would do is obviously what you've got here is the latitude and longitude, and you can store that with your image data. If you're data logging, for example, those of you who are going to be data logging magnetometer data, for example, you'll want to tag your data with that. You can compute it back from the time if you just want to store the time, but I would obviously compute the lat and long and store it as well. Okay. Now the other thing you might want to do is to know whether you're on the light or dark side of the Earth. So, for example, if your experiment is only about nighttime photography, you might want to only take pictures unless we're on the dark side of the Earth. Okay. And basically you just do nothing when you're on the daytime side of the Earth, or the other way around. And the way to do that is you can import something else. We need to import the math module because we need to convert between radians and degrees. Now I'm going to create this object called sun. Sun equals fm.sun. That's the sun. And what we need to do, we're going to use this concept of twilight. And what we do is we're basically going to calculate for a pretend observer who's on the exact location of the ISS on the ground, whether the sun is at below 6 degrees below the horizon or not. Okay, and that's 6 degrees below the horizon is what we call domestic twilight, and then nautical twilight, I believe, is 12 degrees below the horizon. So depending on how stringent you want to be, you can either use -6 or -12. So I'm going to create a variable called twilight, and I'm going to go math.radians -6. So that's -6 degrees below the horizon. Okay. Now we need to create this thing called an observer. Now we're going to do this every time around this loop. So we're keeping this ISS object which we loaded up here, and we're just recomputing it every time we go around this loop. But what we're also going to do, I'm just going to create this observer. We're going to call it, I'll call it obs equals fm observer. Okay, and then we're going to go obs.lat equals ISS sublat, and then obs.long equals, so we're basically setting it to the same location that we've got for the ISS, and then we're going to set its elevation to 0, and that basically, it's not going to be perfectly accurate, obviously, if you're like above the Himalayas and you set elevation to 0, but you just need it to be roughly right to know whether you're on the dark or light side of the Earth. So we're just going to assume that the elevation of the observer is 0, is sea level. Okay. And then what we do is we go sun.compute, and then our observer, obs. Okay. And then we can get the sun angle by going sun angle equals math.degrees sun.alt. And then what we can do is that gives us the sun's angle to the observer in degrees. Actually, I believe that's in radians actually. And then we can go day or night equals day if sun angle greater than twilight, else night. And then what I'll do is I will go, hang on, let's put another, and I'll put %s there, and then we'll just put that into the actual, so now when I run that, what it's going to do, it'll print out the lat and long and say whether we're in day or night. Now, are we near a border? Oh yes, we are. Wow, I timed that well. Right, okay, so let's just see if, I'm just going to double check my code that everything's right. Right. Okay, so currently it's saying we're in the night. And essentially what I'm hoping will happen is when we get to that point in the that might take a few minutes to get there. We should be able to actually watch it change to day when it crosses that day-night boundary. Okay, and that's going to probably take another maybe 5 or 10 minutes for that to happen. So, are there any questions on that whilst we're waiting for the ISS to get into the daylight? There is a link I'd like to share, actually. There's a link which is the full documentation to the Python module, which is this one. And if you go to this URL, it'll be pasted into the chat now. This is the actual official documentation for the FM module. And there's lots more you can do with it. You can calculate the angle of the sun to any planet out there, to other galaxies, all kinds of stuff. It's a really, really good module. But obviously we're just using it to predict the course of the ISS at the moment. Okay. Almost there. All right, so I guess what we can do is we could start going into the submission process. We've already run 20 minutes over, so one of the things... Oh yes, there's one other thing you would want to do as well is you could potentially... what I showed you before about the these pictures, these annotations on the pictures, that's quite a nice thing to actually... the lat and long is quite a nice thing to put into the camera annotation. So let me just quickly run a piece of code which will geotag, wherever it is, it's in FM. Yeah, there we go, geotag images. So here's basically another program which I wrote. I'll just quickly grab the updated telemetry that I've got offline here and pop it into this other program, which is very similar. And then what I've done is basically written a program which tags the lat and long into, what it does, it builds up a string, an array of bits of information that I want to tag into there. And then I use this little clever technique where you can build up a list of all the bits by just appending the information you want. And then if you go carriage return \n .join and then your array, it sticks it all into the a string which will then be the camera annotation. So let me just run this and you can see what I mean. So if I run that now, you see it's actually computing the ISS lat and long as it's running, and that will now be tagged into that picture. So, and there's Foo, me blinking. And then you can see the lat and long is actually encoded into the pixels of the image, which is quite a nice way of doing it. Okay. Now, have we missed it? Have we missed it? No, almost there. It's going to be embarrassing if I've got this wrong.
Nearly there.
Yeah.
A few people have been asking again where the archive stream is going to be put after the...
Oh, okay. I'll just quickly remind people then. So it'll be on the AstroPi website, and if you just come to the AstroPi website and scroll down to the bottom, it's going to shunt these ones across a bit. So Paolo and Tomar is going to be knocked over one, and then the new update will be here, which will give us a link to the archived footage. Okay.
And all the links that we've been pasting, we'll put those somewhere as well.
Yeah, they'll be on there too. Yeah.
And someone's just asked, can you provide a link to the geotagging code you just used? Yeah,
I can put that up. What I'll do is I'll probably put a link to a zip file which has got all the code that we used in this webinar on that update, so that you can see it. Okay.
And someone's also asked, is there a limitation on how much disk space each team's allowed to use?
Well, what we're going to do is we're going to have the ground station remotely connect to the AstroPis from ground and download everything every couple of days. So as long as you don't use up, like, I don't know, 10 gigs or something, you know, we're going to try and not restrict the amount of disk space that people use, and then keep basically stopping the experiments and downloading everything to ground, clearing the disk space, and doing it that way. So hopefully it shouldn't actually be that too much of a problem.
And how much is the SD card? How big is the SD card that's in the Pis?
It's 32 gig at the moment, so most of that space can be used. Right, should be changing to day any time now. There you go, day. Hooray!
Wow, it worked. Fantastic.
There you go. Right, and obviously in 45 minutes, when it goes back into the dark side of Earth, that'll go back to night. Okay. All right, so we're almost there. We're almost at the end. Before I move on from Ephemeris, are there any questions about Ephemeris and tracking and telemetry and stuff?
No, that's it.
Okay, cool. All right. Well, that was kind of good timing of the ISS to be in the right position for us. Right, so we're just going to quickly move on to the submission process. So when you're ready to submit your code, please do as much testing as you can. It's going to be really important to do your testing. So come to the Mission Space Lab page, and then you'll see every time you come here, this bar will move around to sort of keep reminding you how much time you've got left. You'll have to answer 3 questions, okay? And they're listed here. What are the main objectives of your mission? Describe how you will achieve your mission objectives, and what do you think the results of the ISS will be, okay? Now, you don't have to use that max. It's a maximum number of characters that you can use, but you don't have to use the entire maximum, okay? And at the moment, the form isn't there, but if you click Submit Code, it just takes you to a page where the form will become, this page will become the form, okay? And you'll get a reminder email from us to remind you that that's now available, okay? And there is a nice FAQ. If you get any, if there's, always check the FAQ before emailing us, because it may be that it's already on here. This FAQ is quite long now. Just load that. There's loads of questions in here about the mission, about the sensors. You can get the data sheets for the sensors. You can get all kinds of cool stuff. There's some do's and don'ts and stuff like that so always just give this a quick skim, and if anything comes up that's not obvious to you, then do make sure that you have a look in there. There's also the Raspberry Pi forum, which is a good place to get help if you need help. Which, if you go to here, or if you just go to the Raspberry Pi homepage, you just hit raspberrypi.org, go up to forums there, and then if you scroll down, there's the Astro Pi forum, and then you can post in here, post in your questions, and then that user there, Dave Spice, is me, and I'll be I can reply to your questions that way. And this is quite a good way to get technical help. If you've got like a problem with your code's not behaving properly, post the code in here, and then other people who've got Sense Hats and Raspberry Pi kits can actually test it out, and a lot of other people besides myself will be able to provide help to you. Okay. And then if all else fails and you can't find the answer to the problems you're having, email inquiries@astropi.org, and we'll put the link in the email chat as well. And then please also check out our AstroPi learning resources. They're quite useful. Go to the homepage of AstroPi, scroll down. Getting started with the Sense Hat's a really good one. Lots of information in here about how to, getting the orientation, all the different things you can do with the Sense Hat. And then you've got the 3D printed flight case, and then the flight data analysis if you want to look at the kind of sensors that you want to get. You can, when you're on this site, you can actually just look at other projects. If you click on this where it says projects here, you can go back to the root of all the projects and see all the other kind of projects that you can get into. And there's stuff to do with other things that we do that aren't AstroPi as well on there. You can filter on space is a good way to do it. If you just go up to the top and go browse topics, space. And then you get all the AstroPi related ones filtered. Okay, so we are literally almost there. There's also some resources on the ESA Education website which are useful. Let's go back to there, and there on this link will be pasted into the chat as well. So you can come here and have a look at these resources too on the ESA Education website, and there's a whole bunch of them. Okay, and they're really good to look at as well. When you've submitted, what will happen, if I just go back to the Mission Space Lab timeline, because we're currently in this stage, what will happen is during this time window, your code will be running on the ISS. We'll be preparing your code for spaceflight and uploading it to the ISS. And then what will happen is your code will run, and we will send you back any results that you've created. So program your files to create data and save files to get back from space. You'll get those files back, and then in phase 4 you have the opportunity to write a short report on the results that you've got. And this doesn't have to be, this is going to be based on quite a simple template which will have fields for you to fill in, so it's not a hugely onerous task, but we want to know about what you found out, if you see what I mean. And then you'll have until the 11th of June to send in your report, and you need to send in your report to get your certificate. Okay, if you don't send in the final report, if you don't complete phase 4, you don't get your certificate. Okay, and also you can actually, when you get to this stage and you've submitted your report, you can also send off for a Crest Award if you want to, as well, which is quite a well-recognised thing, and it's a really good thing for the students to put on their CVs. Okay. So that's phase 3 and 4. The last thing to do before we are there any questions on the submission process before we move?
Sort of. One question is, will teams be able to find out when their code is running? So if they want to synchronize something with measurements going on Earth, can they find it out in advance?
I will know approximately when it will be running. Basically, I won't know the exact time when your code is exactly running. I won't be able to post on Twitter or anything like that about when your code's running. But what I can do is, what we usually do is we have a couple of Twitter accounts which are actually the AstroPi units. I think it's Astro_Pi_Viz and Astro_Pi_IR. And what we usually do is we make them do some tweets when the code's about to run. So you'll know roughly when all of the batched student experiments for AstroPi 2017 to 18 are going to run, and your code will be somewhere within that window, if you see what I mean. So we won't know exactly until we've got the results, because usually it's down to the discretion of the crew when they start it.
So as long as you've time-stamped your results accurately,
yeah,
and you've started your Earthbound experiment with a wide enough window, you should be able to synchronize it.
Oh yeah, totally,
afterwards,
yeah,
right?
yeah. So yeah, we'll know roughly when it will be. It will probably be late April, early May when it's actually running. Okay.
That was the last question.
All right, okay, so the last thing I want to quickly do before we sign off, I know we're running over a bit, is to go through the coding rules, which seem really intimidating, but they're actually not. If you just this is basically an opportunity for you to ask me anything about any of these questions. So I'm sure you've all got this out and had a look at them. Okay. You know, for example, like, you know, the one about networking. We had one time we had this. I think some young Polish lad. He tried to work out the public IP address of the ISS and then email it to himself, sort of thing. And obviously because when no student code is allowed to use the ISS LAN, we're just completely off limits for that, and all the code runs under an account which can't access the network. So obviously it's not really a scientific experiment anyway. So you know, I felt like emailing him and saying, "Nice try, kid," but no. So if there are any kind of, like, you know, you've got the coding must on one side and the coding must not on the others. We found in previous competitions of AstroPi that quite a lot of code was a lot of submissions were being excluded because they didn't obey these rules. So we've actually now got them on a poster. Okay. Now what you should be doing, but by about like mid-December, January, this ought to be up on the wall somewhere, so all the kids can keep referring to it and making sure that they're not doing anything. And if you just take a moment, get them to read through it. You know, read it out to them if you have to. Because obviously what we've got is some automated tools which can check all the code almost instantly for any violations of these rules. Okay, so please make sure that you obey them all, because if you don't, that's a disqualification. Okay. So are there any questions about any of the rules? Anyone wants to elaborate on what's written in here?
One question is, can we use any joystick movements or buttons?
Yes, you can. But your code can't rely on it. Okay, so basically, if you write a program, for example, that doesn't start unless someone presses a joystick or a button, then your code would basically sit there for 3 hours doing nothing, because the astronauts don't actually have time to actually go and interact with your experiments, because we've got very limited crew time for AstroPi. Most of our crew time is just for getting the AstroPis out, deploying them, moving them to different locations and stuff. We haven't got any time for actually interacting with the experiments, I'm afraid.
And one more, which is, how much of the data processing has to happen on the AstroPi? So I think they're basically saying, can they just log their data with the AstroPi, pull the data back and do the analysis later? Yeah,
you can. That's what I would recommend most people do, because obviously the Pi on the space station isn't the fastest Pi, certainly not as fast as the ones that you've got. So yeah, a good strategy is to just collect data, and then you know, just store it, and then when it gets returned to you at the end of phase 3, you can analyse and process everything on ground. The only caveat to that is the images in in the Columbus module. If you are taking images in a Columbus module, you have to process them in flight, and then discard the images, because yeah, when we analyse your code after it's been submitted, we'll be able to see if you're retaining images after your code is run, and then that will be a disqualification based on the rules. Okay.
And the question, I think this goes back to what we were talking about right at the start about extra libraries and TensorFlow and complicated things like that. Is it possible to write a shell script that does all of the complicated installation and supply that as part of your entry?
Yes, you can do that. That's actually kind of helpful as well, especially if it's a really complicated installation procedure. What you can do is you can even supply deb files if you want to, and we can test those. What will happen is, generally speaking, it has to be something that's already inapt. Okay, there's some exceptions like OpenCV, for example, which you have to download, but it has to be, you know, we will download the source for it and do everything. But yeah, there will actually be a field on this form. If we go back to the AstroPi, the video, the screen output, on this form, that when you go to this page, the submit code page, there will be a field on this form where you can type in all of those shell commands, which can do that. But if you want to include, usually what we do is we have you upload a zip file of all your code and any kind of extra bits and pieces that it needs. You can include the install create a shell script called install dependencies or something like that, and then that will, like, you know, signpost us to look at that, if you see what I mean. Okay.
Yeah, I think that's our questions done.
Okay. Right. So I expect everybody's really tired and wants to go home now. But do we want to do a quick thing about the LED matrix, or is everybody happy?
Our numbers are dropping off of the stream, so.
Okay, right. I think everybody's going. Right. Okay.
A bit tired, I think.
Yeah, everybody's tired. Yeah. Well, it's been about 2.5 hours, so it's the longest one ever.
2 hours 40, nearly.
Yeah. Oh, is it really?
Yeah.
Wow. Okay. Well, thanks for everybody. Thanks for watching. And we'll post the listen again link on the AstroPi homepage. It will appear right here where this Teach with Space icon is, and those two will get shunted across. Okay. All right. Any other questions? Anything else? No. All right. Okay. Well, bye-bye. Thank you very much.
Bye.